Yes, I think we are ready to go. So I will make a very short introduction and then I'll leave you the floor. So we're happy today to have Binbin from Wuhan University. He holds PhD in geocomputation from the National University of Ireland, Maynooth, where he was affiliated with the National Center for Geocomputation, and he is currently an associate professor at the School of Remote Sensing and Information Engineering at Wuhan University. And today he's here to talk about geographically weighted models. So thank you for being here. The floor is yours.
Okay, thank you very much. It's really my great honor to be here, to be in CASA, because it's really a dreaming place for any scholar in spatial analysis and spatial statistics. Yeah. So today I want to be here to give some talk on the geographically weighted models. That's what I was working on in the last around 15 years, and to develop these models and the tools, the software. So this is the outline I want to talk. Is why I should do this. It's about the spatial heterogeneity and what kinds of the geographically weighted models. And there's except the GWR, geographic weighted regression, and there's also some etc. more extensions of the geographic weighted models. And then I will talk about there's two tools actually. There's one R package, and there's also a newly released standalone software called GWmodels. We are releasing. Okay, so let's. So first of all, why we should do this? Why we should use the geographically weighted models? Actually, as I know, before this seminar, I've talked with someone of you, and someone you have used these models as well. So we can see that, for the the spatial analysis or spatial statistics, you will do something. You will deal with the variables, or will deal with the data. And just for example, if you just want to model, the body, the weight, and the head of the person, you can just, to do the regression things. But in practice, you have to, for different people, even different people from different area, or different, the male or female. So you have different things. It means you can just do regression in different groups. And that's how, the BMI, the body mass index, that counts. And there's some extreme example, just to say that's these two variable here, if you want to do regression with them, and you can just do a regression line here. So from this part, you can see what? You can see from these two variables, there's a positive relationship, right? But if I tell you this data are coming from two different places or two different locations, you just, to group them by location. And again, you can do, the regression line again. And you will see what? The relationship becomes negative. It's paradox, right? So it means in the geographic studies, we should focus on some location-wise or spatially varying relationships. That's how the spatial heterogeneity comes. Actually, there's one paper published by Michael Chad in 2004. He proposed there's the principle of the spatial heterogeneity. It means if you want to model the geographical variables, or if you want to model the data relationship, if the study area change, you should, your results could be also changed as well. So that's how the spatial heterogeneity. Okay, so later on, we come to the popular technique recently, actually, since from, I think it starts from 1996. In 1996, Chris, Stewart, and Martin, they proposed a technique called geographic weighted regression. And this is the general expression of the GWR technique. Just look at this formula. What's the difference between the GWR and the traditional linear regression? So you will notice that the main difference is here, right? It's Berkeley's UIVI. UFEM means the spatial coordinates. It means like the coefficients will be the function of the spatial coordinates. Instead of, from the linear regression, you will get only one, like one set of the coefficient estimate for the whole data set. But from the GWmodel technique, you can get location-wise coefficient estimates. It means like, the procedure is really like, straightforward to go. It's at the beginning, you just predefine some like regression points, different locations. For different locations, for this one, you just calculate the distance, the proximity, and then you calculate one like the spatial weight matrix. And then you use weighted least square, the technique, just to estimate a set of the coefficient at location I, at this location here. And then finish this, you move next. Again, repeat. Okay, in this case, like you will get what? You will get like for different locations, you will get different coefficient estimates. That means like you can use the location-wise coefficient estimates for modeling the spatial heterogeneities. Okay, so the key part will be like how to calculate the spatial weights, like how to make the coefficients vary. Okay, so here, like, we provide some, just the kernel functions. Kernel functions means like, just some rows or some functions to define how the weights will change alongside the distance. It's the key role will be distance decaying. It's like, it comes from the first law of geography by Walter Tobler. It's about spatial dependence. It means like, that if the spatial objects are more like, they are near, the influence between them will be like there will be more influence. Okay. So here, like for different kernels, you can use different kernels to calculate the weights. Just for this one, if regardless of the distance, you will always get, the weight will be 1. It means like what? It means you will get the global model, right? It's no difference between the linear regression and the GWmodel technique. But if you use the Gaussian expositional box plot, bi-square, tree cube, etc., you will get what? You will get like spatially varying relationships. It means like, for each location, you can get, the varying spatial weights. Just, the coefficient will change as well. Okay, this how, the basic GWmodel works. And in 2019, at that time, I think there's 1 week I just was free from work. I just did some boring things. I just, just to get all the papers on GWmodel from the WOS, Web of Science, the database. Okay, I just Google, search all these articles and I mix the the keywords co-occurrence map graph. You can see for different like domains, they apply GWmodel technique just to explore the spatially varying relationships. Select the epidemic, environmental studies, climate, biology, socioeconomic, etc. And you can also see the the word cloud, different keywords appear. So that means like the GWmodel technique is becoming like more popular, and people are using this technique just to explore the spatial heterogeneities in data relationships. I just want to give you a very simple example. I'm from Wuhan. Currently, I'm working in Wuhan University. I think everyone know Wuhan. It's in 2020. Okay, at that time I was locked down. I was locked down in Wuhan for I think it's 5 months. In the building. Okay, and but I did one thing because that time I was very nervous every day. You see, it's really you don't know what's happening outside. Okay, so before the lockdown, there's 1 week, because that time is like everyone know in China there's a big festival called Spring Festival. Okay, so people are traveling back home, and before the lockdown, there's 1 week. 4 million people, 4 million population just going outside Wuhan. You can see the population flow. Okay, so there's one paper published in Nature by a professor from University of Hong Kong, and he published this. He just want to explore, what's the relationship between the population flow and the COVID-19 cases. Okay, and he used some the OLS, the linear regression, just to do the regression between the COVID-19 cases and the population flow from Wuhan to the other cities. And he released the data. Okay, and we just use the data, just run GWR. And we'll find what? We'll find these things. You can see from the R-square value, this is the OLS linear model. This is the GW model. It means what? It means it has the much better, it's like more hair. So hair R-square values means it interprets the results better. Just from the maps, you will realize some really interesting thing. Because the population flow from Wuhan to the other cities, the most the cities are mostly influenced is the cities within the Hubei province. I know yes, there are some Chinese students here, and Wuhan is the capital of Hubei province, and so most of the people working in Wuhan, they are just from the from the cities within the Hubei province. Okay. So you can see these cities within Hubei province, they are the mostly influenced. But there are some weird things, but I can't even, until now, I can't interpret them why. Because here you can see really, really high influence in these cities. But from this map, from this example, it means the GWR technique, it can explore really spatially varying relationships between geographical variables. Okay. It can give you much better results in compared to the linear regression model. Okay, from the basic GWR, we move forward. And there is another thing. It's if you get the multiple variables in your model, the different variables, look at these three maps. When we calculate the spatial weights and the bandwidth, there's a key concept called bandwidth. Bandwidth means how will you control the width will decay. Okay, if you get the larger bandwidth, the width will decay slowly. Yeah, if you get the small bandwidth, it will means the width decay very fast. Okay, so from this, the bandwidth, the larger bandwidth, the medium bandwidth, and the small bandwidth, you will get very different coefficient estimates. Even you get the same model, same data, but you get very different results. It means different size of the bandwidth, it will control the spatially varying scale of your coefficient estimates. So let's make another idea. It's when you get multiple variables in the model, it will vary differently. It must be, yeah. So for example, I've done many case studies with the house price data. House price, they will change because of, some of them, they will change it because the property is near to a railway station, okay, to the bus station, et cetera. But some of the house, it's because, it can get access to some really good primary school. Okay, and also, it could be also affected. There's some policy, the Chinese government will issue some policy to control or to affect the house price, the limitation. You can only buy one property for one family in the city. Okay, it will also affect the house price. So see the different variables, if you put them all in the same model, the spatially varying coefficients could be very different because the policy will be for the whole city, not for this area or for the different areas. It will be the same. But for the really local features, the property is near to a railway station, or it can really get the good view from the river or from a lake or from the park. Okay, so it will give you some really different things. So there's another idea is how can we control, the coefficient estimates? They should vary differently. Okay, there's another like technique proposed by Chris in 1999, and called mixed GWR. Mixed GWR means like you can control your variables. Some of the variables will be global, means no, it won't change. For example, the policy will affect the whole city in the same degree, not really vary. Okay, but some local features they will vary across the study area. Okay, you get some spatial varying coefficients and you get some global ones. Okay, but move forward is there's another my classmate Binbin, and she was doing her PhD topic on the GWR with flexible bandwidth. It means like you can use a specific bandwidth to control the varying scale of the coefficients. Okay, when the time moved forward, and in 2017, it's really a year for the multi-scale GWR. Absolutely, in that year, 3 papers, new papers, it's like one is from me, and we published together. It's like almost at the same time about how to control exactly how to control your geographically weighted regression model with varying scales. And in this one, in my paper, it's like to control the changing of the varying scale by the distance metric and the bandwidth. It means like why distance metric? Because my PhD topic is on how to improve the GWR calibration with non-Euclidean distance metric. Why do that? It's actually it comes from London. The London Thames River. Okay, alongside the Thames River, there's two. Suppose there are 2 houses, just 2 sides of the on the 2 sides of the Thames River. The Euclidean distance will be very near to each other. Okay, but the price difference will be very big because they are just on the 2 different districts. Okay, but if you consider the natural distance, not the Euclidean distance, it will just like give you the correct view on that. Okay, so that's why I just want to use really like the distance metric and the bandwidth to control that. Okay, but overall, all these 3 techniques are just like tell you how to control the scale of the varying coefficients by bandwidth or by this metric. So that's why that's how the multi-scale GWR technique comes. So later on, just for give you a very simple example, is just to do some simulation data set. We simulate, the beta 2 is spatially varying, but the beta 1 is not spatially varying. It's just it's global. It won't change. But if you use the GWR estimates, the beta 2 is fine, but the beta 1 is still have some spatially varying patterns. You can see that. Definitely it comes from, there's another one called intercept, or called some like the errors, residual errors, random residual errors. Okay, so multi-scale GWR just give you really like just the make control on the bandwidth and on the distance metric. It will really give you the beta 2, the beta 1 will be, you can see the green line. The black line is the real value, but the green line is the results from the multi-scale GWR. It's just automatically give you the correct results. It won't change. Okay. And also, like I think before 2015, there's some problem with the GWR technique. When people are applying the GWR technique, they are not really using it correctly. Sometimes like we think the GWR technique is wrongly applied because some conditions you should consider when you're applying the GWR technique. So that's why I think it's last year with Lex Comber, and we published one paper on to teach you how to correctly apply GWR technique. And this is the flow map, and we just agree with each other. Is multi-scale GWR should be the default or the first choice when you get your data set. because there's another paper in 2018 I published in CUS. And just found really interesting thing is like when you get a model, gets the data, whenever whatever you change the kernel function or change your distance metric, the kinds of the bandwidth size won't change. It's just comes the same. Okay, it's always the same. It means the best scale of the coefficients variations, it will be kinds of fixed. You should find it, and you can get some really good results or the correct things. Okay, so for the multi-scale GWmodel, we apply it with a data set of Wuhan. Wuhan, we have the community level data sets, and we get the average house price at the community level, and we got some really environmental and socioeconomic variables, and we want to apply it with the multi-scale GWmodel. And we have 2 years data. It's 2015 and 2019. Okay, and we just from that we choose just from the correlations between the variables, we just choose the different variables inside. And finally, we selected 5 variables in our model. And I think what I want to show you is for the benchmarks, we include basic GWmodel, SLM, LR, and multi-scale GWmodel. And finally, we got this. Look at this table. It's really, when I first time I submit the manuscript, and the reviewer give me a comment, it's like, your results is too perfect. Look at this. Of course, the perfect is with the quote. Let's look at this. The linear regression is here, but the multi-scale GWmodel regression result is here. It's like it's 0.9 compared to 0.1. It just gives me a question about, how will you verify your model is not overfitting? Okay, so that's a problem because I just chat with the people, and they also encounter this problem. It's like sometimes if you got too small bandwidth, think about this, too small bandwidth, it means like you will get really very few observations to involve in your model collaboration. It could cause the overfitting problem. I think it will be a common problem when you apply multi-scale GWmodel or GWmodel. Okay, what I do is I just use the cross-validation thing. I just take the observation with the weight 1 out, take them out, and to say if it's overfitting, it means really the local observations will affect your model a lot. Okay, but if it's overfitted, and when the observation is taken out, your results will just it will fluctuate, right? The results will change. But finally, I just verify this by the cross-validation to say, okay, there's not really overfitting, but only a few of them, you can see, very few of them, 2 or 3 points. Okay, so for multi-scale GWmodel regression, what you will get is for different coefficients or different parameters, and you can get for example this one is the green rate. It means the rate of the green land is around your house. Okay, and you can see from the 2015 to 2019, the people are they will evaluate the house price. It's more on the environment around your house, around the property. But look at this, it's the density of the POI, the point of interest. It means the validity of the community around your property. But you see what? Just compare these two maps, you will see it's absolutely different scale of the variations. Okay, from this map you can see a lot of the variations, but from this map you can, especially from this one, you can just see 2 patterns just alongside. This is the Yangtze River. Okay, but this side will be absolutely 2 parts. Okay, so that's how the multi-skill GWmodel will give you really different things. And also, what I want to say is like this is intercept. Intercept means what? It means the location gives the value to the property. Finally, this is the average house price. Is on average is around like 12,000 yuan per square meter. But if you take them all out, like the grain rate and the GDP and some like the density of the POI, and for the intercept on the average you will get, I think it's around like 10,000. It means what? It means like the most part or the main part of the value of a property is location. It's location. Actually, yeah, just you buy a property, the primary thing will be location, location, location. You just select the location. It gives you the main part of the value. So that's how the thing. And then when we worked a lot on the house price data. That's the community level. Yeah, we got the data from the different ways. And there's a website called Baker. Yeah, some Chinese students know that's the Baker. Yeah, we got the data from the Baker website and second-hand property. You can see across Wuhan, we get around like 20,000 second-hand properties on sale. Okay, but this is actually a neighborhood. Okay, we can also call it block. Okay, in Wuhan, because block is a fundamental unit, because like for example, for one block you have a few of the buildings belong to this block, and in Wuhan we will have walls just to separate this block from outside. Okay, so the problem is like we got the data, the property, and we only know what? We only know this property is from this block, but we have no idea where is it. Is the property is here in this building or in this building? No, we don't know. But in which block we don't know. Okay, but it will give you a problem. Is what? It's like we have 20,000 points, but we only have what? Only have around 800 blocks. It means 20,000 points will share only 800. We share 800 different locations. Okay, so that will be a problem. Is like you will get this, all these things. Means like hundreds, maybe more than 1,000 points. They have the same location. Okay, so what I do is like we got the second-hand property data, and I want my students to apply the GW technique. Okay, you see, it's like we want to explore whether we can use GW technique to explore this. You can see what? You can see do this. First of all, you have to optimize the bandwidth. And you will get this, the cross-validation score and the bandwidth, you will get this. It means what? It means like just imagine that, you just use one bandwidth, like 1,000 meters, okay? And when you use a larger, like bandwidth, like say 1,100 meters, just a 100 meter, just larger. And then maybe you include one more new block in your in your local calibration. But you means that there's a very large from Wuhan called Beijing. Okay, it's kind of like maybe like 1,500 properties are on sale at the same time. It means like you just go very little distance or bandwidth size, it will give you another like 1,500 points will be coming into your model. And in that, like for the same block, even for the same block, the different property, it will have a very different price, because different levels, different floors, in China, we all know that, Wuhan is a very humid city. Okay, it's a lot of raining, et cetera, et cetera. And, when you get the lower floor, it's cheap. But if you get here and here, the price is just going up. Okay, it's going up. But in the top, it's again down because Wuhan is really hot. If the top floor, your room will be really like, steaming in the summertime. Okay. So that's why, it's like even in the same building, but even in that block, sometimes in Beijing, it's really a weird block because, there's another factor will affect the house price a lot. Like, for example, if you buy this property, you can get access to really good primary school. But for the same block, they have two different policies. Like for these buildings here, you can get access to the really good primary school. But for this part, no. So yeah, I know, but yeah, it's a policy. So it means like even in the same block, the price change could be 20,000 yuan per square meter. Okay. So it will be really a big change. It means like, it will give you some really weird results. Okay, in this case, the basic GW won't work with the data set. Okay, so what we think about this, there's another technique called the hierarchical linear model. Hierarchical linear model means like you have the grouped data. You have the grouped data, and you can do this, hierarchical regression things. But for example, like, for different groups, you can just do regression, okay? But think about this, we just group the data by location, okay? It's naturally will give you different levels or different hierarchies of the data. So that means like, we developed a new technique called HLM GWR. It means like for this type of the data, first we will group them. We will define the variables into two different categories. Some of them are grouped, means like grouped by the locations. Some of them are sampled. It's like, just use the hierarchical linear model. And for this model, we just developed, actually, at the beginning, we just used really simple calibration algorithm. We just use two steps. First one, we just calibrate the sample level variables via the HLM model. But later on, we just again apply the GW model with a grouped level. But it's not really scientific. It's not a rigorous algorithm. So later on, this paper just came out recently. I think it's this month, in IGJS, and we just developed a new called backfitting and maximum likelihood. And where this algorithm, you can calculate the HLM GW model more precisely. And in this case, with the data, with the second-hand property data, and we can just calibrate the model well. Yeah, I should go quick. Okay, so this is the new extensions on the new inputs from us in the GW technique. But for GW technique, just concern about this. Regression is just a type of the statistical technique. We have a lot of other, some other types of the technique. So just think about this. We make regression as some generic function model. Okay, so we just use this location-wise calibration, and we just calculate the statistics, and we just use the different functions. That means we can just get a really wide range of the techniques instead of only regression. Okay, so that's how GWmodels could be a locally modeling framework instead of a single technique. Just for example, for some summary statistics, we just make them connected to the location. Okay, just for a very, very simple example is like we got the aging population from the census data of China. It's 2010 and 2020. Clearly you will see what? You will see the aging population is much increased. Okay, so we just do this. We want to just explore the potential relations between the aging population and some economic variables. But with the correlation, like global correlation, you can just guess this. For each like the aging population and between the GDP, between et cetera, you just get this. This one, the correlation coefficient will be minus 0.12. Okay, but with the the geographically weighted correlation, you can get a map. It means like it's really interesting. It's really interesting. We always say the Chinese population. There is a very famous line called Hu line. Yeah. Line, just like this, from the west part and the east part, very different. Okay, even from this, you can say the western part and the eastern part, they have very different relations between the GDP and aging population. It will give you a clue, to dig into why you should explain, why this pattern appear. Okay, so. Another thing is like called principal component analysis. We all know this technique, but like if just as a statistical technique, you just have nothing to do with the location. But we we use some the local variance covariance matrix. We just do this to the location-wise thing. We will get the location-wise local eigenvalues and local eigenvectors. And with this technique, we recently, I think it's not recently, this work is published recently, but we did this work is 2 years ago. It's like this, we just model with Wuhan, for a city, land resource is the most important part. And we just want to say, what's the the land resource carrying capacity. Okay, and we collect a lot of the variables, including the population, economic, construction, transportation, etc. But if you do studies with such a wide range of the variables, you will always get a problem is how to make a comprehensive index from these indexes. Okay, it means like how to integrate or how to compute the integrated index. And we pick 5 variables from all these variables, including the population, GDP, etc., plot ratio, representing the construction. Okay, we do this, but we only say these are single indicators. We just, to say, for example, this one is just like, we just look at the city and where is the population summit. The population is high here, low here, etc., like this. But we can't say, okay, land carrying capacity. But how can we get a comprehensive index? I know we have some other like a technique, like AHP, like entropy weighting approach. Okay, I think that's the most straightforward way. But with the GWPCA, we just develop a new way. Because just think about this, the land carrying capacity means like the land of the city or the urban land should be developed in different ways. Because some of the area, like in Wuhan, some of the area are just for the residential land usage. But some of the area are for the industrial. It's like, there are some big companies of the cars in Wuhan, just around here. But and also some of them are, for some like the new techs. Okay, so for the GWPCA technique, it will give you some spatially varying like weights, just to make comprehensive index from all these single indicators. And this is the map we got. It's called the comprehensive carrying pressure. And it's really like give us a really straightforward, it's very good view on this. From this map, you can see the head is around here. But if you're familiar with the geography with the Wuhan city, you will see this is the most central part of Wuhan. But Wuhan is really it's a complicated. It's like many places. It's huge. But from this part, yeah, it's the head is the land carrying pressure. Okay. So it's really, and also we just apply this technique to different scales, like the sub-district level and the grade level. Okay, and also we will see that it's especially varying factors will affect your index. It means like some of the area is most of the area is like affected, land carrying capacity is affected by the population. Okay, but some of them are not. It like the GDP means like industrial area, okay, etc. But okay, I should quickly we come to this. The GWmodels it could be a new like a technical framework. It means like from the descriptive analysis. Oh, okay. I just divide them into 4 levels of the analysis. It's like for example, like you can just use your spatial data to describe it. Okay, you can use the GW summary statistics. Okay, and also you can do some exploratory data analysis, and with GWPC or GWR, etc. And also when you know exact relationships between the variables, and you can if you want to try to interpret, how the relationships, you can use the GWR, multi-scale GWR, etc. And then you can do predictions or simulations. There are some new, like, GW techniques by some other teams called GWAN, means like, they integrate the artificial intelligence techniques with the geographically weighted scales. Yeah, all these I talked about is like, since I finished my PhD in 2012, and then I started the postdoc job there from NCG, and from that year I started to develop one package called GWmodel. Okay, GWmodel, and after until now I think we have 65 versions to evolve this package. Yeah, it's really a big job. Yeah, you can see all this pink color. Pink color means like it have included all these functions in the package, including the lots of choices of the GWR technique, multi-scale GWR, and robust GWR, and also GTWR space-time. Okay, and these gray ones, I'm working on that. Okay, it still need time. Yeah, it will cost my whole career, I think. Okay. Also, there's a new feature I want to release here because I just now I located in Northwick, Rosam State in Northwick in Devon, and it's really in the farmland. It's really quiet, but I can do something with the package. And recently, I just take 1 week just to replace. Roger Vivant is a big name in R, and he retired, and he also retired some packages like map tools, and all these about the SP things, spatial objects. So what I do is like, the now in R is really popular is about SF, simple features. Okay, I just, to do all the functions, just to support both spatial and SF. It means like you can just use R, use the spatial objects and SF objects. You can just, it will automatically detect it and you can use it. It's really handy now. Previously, it's really, it's not easy to use it because, you have to convert the SF object to the spatial object, but it will always give you an error. Yeah, it's like, it's a problem. And for R, okay, we're still talking about the R. R, they have the limitation. Yes, I know, most of you have really, really good laptop or good PC, but in R, they have the limitation of the maximum, like the volume of your matrix. Okay, it's like around 2 gigabytes. It means like whatever you get your laptop, maybe it has like a 16 GB RAM, but it won't work. If your matrix, the size of the matrix is larger than 2 GB, it will give you an error. So it also, puzzles us a lot because, the data sets, the data volume is getting larger and larger. Okay, I think it's 3 years ago. I always get email from users. They say, okay, the GWmodel is not working because I have 10,000 points. It's not working. But we calculate it's maximum. Theoretically you can have 16,000 points to be calibrated with with R. But when you get more than 10,000, it will be a problem. Okay, what we do is start from the 2012, 2022, I think. Yeah, we're just working on this just to improve the computational efficiency of GWmodel. Okay, what we do is first thing is we just improve the storage efficiency. We make it to n squared to ONM. It means the linear is m is the variable, is the number of the exploratory variables. Okay, and from this part, it means like we can got a much larger volume of this. And also, we apply some different strategy of the parallel computings. Okay.
They have to.
Oh, okay, yes. No worries. Thanks. Thank you for coming. Okay. We just use some multiple thread computing. Just means like you can use your PC to do parallel computing with GWmodel. And also, like if you get really good machine, it's like you have the GPU in your machine, and you can use CUDA, and just to do this. And we improve the computational efficiency, and then we got, because for the multiple processor, all for CUDA, it's different strategy. Because if you want to do parallel computing, you have to how to define how it be paralleled. Okay, you have to collect the data or distribute the computational tasks for the different strategy, and we just design different strategy just to collect data and to distribute the tasks. And then we got this. We compared to some really this is the GWmodel before, before it's improved. This is the GWCUDA, this is GWMP. And when the data volume goes, larger than 100,000 or maybe larger than 1 million, only GWCUDA works. It's like, the other, just the, GWmodel and GW in Python and fast GW, they also disappeared. Means what? Means like now we can handle more than 1 million points. That's really a big, it's a really big thing. Yeah. But we also get some problem. We just think about this. You have the GWmodel package, but you will have, if you want to use the GWmodel package, you have to program with R. But I know, yeah, in this room, yeah, most of you are really good at programming, but in some other domains, they can't program with R. Yeah. So what will you do? And also in R, it's not, you have to configure. You have to make a very complicated configuration if you want to use GWCUDA or GWMP. And so that will be a main problem. And also, in R, it's not that easy to map to data processing. Okay. So what we do is like when I was locked down in Wuhan, my team have nothing to do. Okay, during that period, I have nothing to do. I'm always it's panic. It's really awful. But I decided to start a new task for my team and for myself is to develop a new thing. It's a new software called GWmodels. GWmodels means we just use the C++ language and the Qt just to develop a new one. And it means it can interpret this. It's like we use we also borrow some APIs from QGIS, and we can do this to view the data, to just to manipulate the data, to process the data, and also for the good thing is like for all the GW models, all the tools, we just design this, the interface. It's really handy to use. You just click on this. Yeah, you just select the layer and select the variables, and then click on OK. And for all the GW models, we design the interface accordingly. And you just like when you finish configure the interface, you just click on OK. It will give you the program of the progress of the computation, and then finally it will give you the results from here, from this interface. Okay, and it will just store the summary file here, and you can view all these things. And the other good thing is like it will automatically detect your PC configuration, and you can configure what's the parallel computing strategy you will use or not. You can just choose it, and you can just depends on your computer. Okay. And then there's another good thing is like when you apply GW technique, you will have a problem because you have to make a lot of maps. Yeah. And we did a thing I think is really interesting is like we did a batch mapping tool. That means like whatever you have the variables to map, and you can just like set a layout, and you can just include all the variables here. You can just change the colors, the symbols you want, and you click OK. Just OK, and it will just save all the high resolution images and the folder you specify. It means like you can make maps, 20 maps at the same time, and with all the same layout, but with the different, of course, with the different colors, symbols. Okay, so that's why we started another development of GWmodels. But the other thing is come to me, it's like I work in Wuhan University because the working pressure is really high. So I really, it's really tough for me, to maintain all the products at the same time. GWmodel R package and the software. It's really a tough job. So I'm thinking about this, we have all the core functionalities in C++. So that's why, I decided to take all the C++ code and to this one. We developed another, actually, we just packed another C++ library. And my target is like, once I got this library ready, later on, I just update this library. And all the R package and all the software, it will use the same core library. Okay, I just update this and all the products will be updated. That's my dream, okay? We're doing this. Actually, I'm finishing this library. And also, like, we also developed some like cloud computing app. It's called Open Geospatial Engine, OGE. Yeah, it's a new engine from Wuhan University. And I just like, I also want to integrate all these things into that cloud computing thing. And you also, what? It's like when I get all the C++ code, now it's really easy to make even R, even Python. From C++ to Python is really handy. You just write a wrapper. It will be a Python library as well. But we didn't do that until now. We have R, we have the software, and we have the cloud computing. You still need time. Okay. Okay. So I should. Oh, sorry. I talked a little bit long. Okay. I'm very sorry. But yeah, just to end this talk. It's like there's a family of the GW models. That what I'm working on is not only on the regression technique, GW technique, and also what I'm working on is like just to extend this technical framework into a wide range of the models. Okay, include into different like analysis levels. You can deal with, other things to map or to model, to analyze your data with, concerning the spatial heterogeneities. All these things with the, a family of the GW models. And I believe, you can find, if you can always find a model suit to you, it will be perfect. Okay. And then also, we are trying to make these two products better and better. And also, like, I think there's always a problem for me. It's like, I did a lot of algorithm or like did a lot of development. But for me, it's like, because my background is on mathematics and it's on like GIS, all these things, development things. But what I need is like, I want more case studies, because if we want to like make it better, it means like you have to apply or use it more and more in more and more cases. Okay, so I'm quite happy, like, to be here to give this talk. I hope, I will get some really, really like, good feedbacks to improve the products or improve the tools. Okay, thank you very much.
So since it's already past 2 p.m., I would say just one or two very quick questions. And if anyone has more questions, they can stay a bit longer after the session. So I would open the floor to questions. Does anyone have?
I'm just curious, one of the maps you showed where it was like a China, Eastern, and like a Western.
Yeah.
What was the actual reason? Because you said that people would know, but like, I don't know.
That's a big question for me, because actually I use it just for example with the usage of my tool. I'm not really like, so yeah, I'm sorry, I didn't consider it a lot. I just assume, the different scales of the things. It's funny, yeah. I think, if we want to really know the reasons or the internal relationships between them, we have to apply, because that's only like the correlation.
Okay.
The correlation means like, it's just correlated. Yeah, it's not really like, the relationships between them. So yeah, we should apply some other, the GWmodel technique with it. Yeah, it will be more clear. Yeah. Okay.
Okay. So thank you very much for the talk. I was one of the user of the R package and also the software. Thank you very much. And I want to ask a question to like, how do you view like the actual results of the GW model? Like when you are doing GW regression,
Yeah.
like you would like normally you would expect the regression to give you some prediction to the actual result. And how do you view that? Like how does GW model performs in that aspect? Like because I think I've read GW model application in many fields, like GWPCA, GW
Yes.
and even if recently there are some GW random forest and GW
Yes, yeah.
boosting
Yes.
applications. That's none of them are actually giving actual like prediction of results. Like how do you like view all that?
Prediction results, you means like estimations of the
Yes.
responsible variables.
Yes.
But yeah, in our package or in the software, the y hat means like, the estimations of the responsible results will be returned. Yeah, it will be returned to you. Yeah, you can visualize it. Yeah, it's there. It's there. But yeah, it's called y hat in your results.
Okay.
Is that if I'm correct? Yeah. But you mean like if you want to evaluate the accuracy of like, the performance of the model, you can look at, the ASCC, like, accurate information creation, all the R square value, all the, residual sum of the square, and you can visualize them. And you can just compare it to the linear regression or to some other benchmark like models. Yeah. It will be I think it will be, yeah, you can compare them to each other. But be careful with one, is like in the package, we use the ASE, but in the, in some other R package, they also use the ASE. But to be careful, the calculation with the ASE could be different. It's not really like you can compare them directly, because, I know, yeah, from the LM function, they also calculate the ASE. But the ASE value is different from the ASC value from the from the GWmodel package. Yeah. So you should be careful with that. But yeah, we will return the linear regression, the diagnostic information from both linear regression and the GWR, and so you can compare them directly because we just to ensure they are the same. Yeah.
One last question.
So you already have your question. So if can we have locally different kernels? So instead of setting up one kernel for the whole system,
Yeah.
can we have locally different?
Yes.
And
Yeah.
how do we perform a sensitivity analysis in order to select the family?
Okay. The first question is like the kernels.
Mhm.
In R, you can't. In the software, you can.
Okay.
Yeah, we make it like, it's kind of like if you don't know the software well, yeah. But if you just look at the software, it can specify different kernels to different variables. Yeah.
And the bandwidth, how?
The bandwidth is, it will be optimized automatically if you just if you want. We have some approach like cross-validation or the ASCC approach. You can just we use the Gaussian selection algorithm just to optimize the bandwidth for you.
That's part of the process.
Yeah, but of course you can specify the bandwidth you want. Yeah, but it will be optimized if you just do nothing with it. Yeah.
Okay, I will close the session. If you have your following question, please feel free to stay a few minutes and have a chat after. So let's thank me a minute with the last one.
So you treat